Yeah, so can you see the presentation?
Yes, sir.
Okay, fine. So first, let me introduce myself. I am Moina Ghoshal. I am doing a PhD in IISER Kolkata, IISER Kolkata, and I am a TA for this course, NOC 23 CY09, which is Fundamentals of Spectroscopy, which was the instructors was Professor Sayan Bakchi and Professor Anirban Hajra. And first of all, this is the very first week assignment. Some questions I will be solving, which will be beneficial for you all to solve questions regarding this in for you. So I will solve questions one by one. First I will give you guys to answer this, or to do some mathematics or whatever it needed. You do that, then you tell me the answer, and then I will solve this. Okay, and if there is any query, you can stop me anytime, anywhere. Okay, then unless you are fully clarified, you can ask me anytime, in multiple times, anywhere. Okay, so very basically, what Professor Bakchi and Professor Hajra have has given lecture on is, the first lecture is basically about what is spectroscopy and what is a spectrum. See, wherever you go, where I don't know if some of you are research scholars or not, or you are in BSc or MSc, wherever you go, you need spectroscopy. In chemistry, you need spectroscopy. Without spectroscopy, you can do anything. You can't do anything. Okay. So if you are going through, suppose you are synthesizing a compound, you want to characterize it, you need some spectroscopic tools, right? So by that way, spectroscopy is very much important. And what is spectroscopy? What does spectroscopy means? Spectroscopy means the interaction of light with matter. Fine. And by that we get a spectrum. But by analysis the spectrum in a correct way, we can conclude our relevant information from that spectrum. Okay. Then Professor Hajra has explained about, sorry, Professor Bakshi has explained about this light matter interaction, where there was two different school of thoughts. One thought light as a wave, another thought was light as a particle. Okay, that will come after this, after the lectures. So particle nature was actually proved by Einstein using this photoelectric effect, where he has irradiated some a light on the metal surface, and electron ejection was observed. And then also Compton effect was there to prove that light has a property of particle. And wave nature of light was proved using interference. From interference, there are two waves. When two waves meet into each other, they can interfere either constructively or destructively. And light shows those properties. So that's why there was a concept of wave particle duality for the lights. Okay. And then he has introduced the concept of radiant energy density. Okay, which is no, so radiant energy density, which he has explained. So it actually gives you idea about what energy density is, what in a density of light is falling on a substance, and that you can relate with the Planck's equation, Planck's black body equation. That will be also important in the next coming slides. And then they have discussed about the concept of absorption, stimulated emission, and spontaneous emission. So see, in spectroscopy, these two types of spectroscopy could be there. Like main one is absorption spectroscopy, and another one is emission spectroscopy. Okay, absorption means there is some electron is absorbing light, so this is going to the upper state. It is the absorption, and it is coming back to the ground state by emitting photon. This is the emission. Okay. So but this emission can be of two types. It could be spontaneous, it can happen of itself, or it could be stimulated by some light energy. Okay, so this when there is a stimulation of light, we call it stimulated emission. And spontaneous emission, what I have told about, that it is the spontaneous emission. You know the meaning of spontaneous, it's happening randomly, or it is happening all of its own. In lecture 2, Professor Hajra has explained the postulates of quantum mechanics, basic quantum mechanics, and he has introduced the concept and properties of wave functions. You know, in classical mechanics, whenever you are going to describe some function, you can describe it, or you want to describe a particle, you can describe it using momentum and position. Okay, but in quantum mechanics, you cannot do that. For this, you need to have something which gives you the information about the particle, and for this, wave function was introduced. And he has explained also the concept of operators and different types of operator and their properties. And also in the last, they have explained. He has explained the Dirac notation. Okay. And in lecture 3, he has explained about eigenvalue and eigenfunctions. What is eigenvalue and what is eigenfunction? Also, he has shown how to calculate average value or expectation value. He also have shown the concept of time dependent Schrodinger equation and also conservative systems and stationary states. Okay. In lecture 4, there was a simple quantum system that was taken to explain all of these things. The system was a simple quantum model, that is a particle in a 1D box. Okay. And then he has calculated the energy, corresponding wave function, and also the normalization constant. Also, calculation of average position and momentum was done for those systems. And also, if time dependency is there, what will be the change in the wave function, which another part is coming in the wave function, he has shown. And in lecture 5, there was calculation on Einstein A and B coefficients, and in Professor Bakshi has explained this about this Einstein A and B coefficient, how they are related, to this radiant energy density, and also he has shown the conditions to obtain absorption and stimulated emission. In what condition absorption will predominate, in what condition stimulated emission will predominate. Okay, and then he has shown the selection rule for electronic transitions. Okay, so let me join. Someone is trying to join. Yeah. So I'm going to the questions. This was a very brief introduction of what has been done in these 5 lectures. Now this is the first question. What is the quantity that contains all information about a quantum particle at a particular instant of time? Which quantity, what is that quantity which contains all information about a quantum particle at a particular instant of time? What I was saying to you that whenever you are in classic, you are doing with classical mechanics. In classical mechanics, you can completely define some particle with position and momentum. That's enough. And from Newton's law, you can calculate everything about the particle. But in quantum mechanics, you need some quantity, or you need something which will describe the particle or particular instant of time. What about the particle? What is the behavior? All it will be describing. So this could it be the Hamiltonian of the particle? Could it be the wave function of the particle? Could it be the position or momentum of the particle? Or it is the Schrodinger equation of the particle? So I want 1 or 2 answers for this question. Anybody?
Sir, the wave function of the particle.
The wave function of the particle, correct. So you can find also the reference in lecture number 2, where it is mentioned clearly that the wave function of a particle actually says everything about the system. So whatever I have told you, first I am going by option. First is a Hamiltonian of the particle. Hamiltonian, okay. Hamiltonian. Do you know how Hamiltonian is represented in quantum mechanics? By which symbol? Okay, so Hamiltonian in quantum mechanics is actually described by H with a cap. Okay, so it is just the energy operator. If you have followed the lectures, there Professor Hajra has clearly mentioned that if in classical mechanics to compare to quantum mechanics, in classical mechanics for every observable, in quantum mechanics there is an operator. For every observable you observe, there is an operator. Okay, so is in this in quantum mechanics, this Hamiltonian is used for to give the energy, to give the energy. Sorry, sorry. So this is the energy operator. Okay, so to get the energy you need Hamiltonian. So Hamiltonian of a particle, from Hamiltonian of a particle you can get the energy of the particle, but at particular instant of time all informations you cannot get from the Hamiltonian of the particle. Okay, now I am just skipping the second answer because it is the answer you have already, you don't know already the answer. I am going to the third point, which is nothing but the position and momentum of the particle. For classical mechanics, it is possible to know about the particle from its position and momentum, but in quantum mechanics you cannot describe the particle from position and momentum. Okay, and also the Schrodinger equation. This fourth one is Schrodinger equation. Schrodinger equation. Please ignore my handwriting. I know it's very poor. So can anybody tell me what is the Schrodinger equation? Anybody? Am I audible to everybody? Can you?
Yes, sir. Yes, sir. Yes, sir. H cap psi is equal to E cap psi.
H cap psi equals to off. Yes, you are correct. H cap psi is equals to E cap psi. E cap not, no, it is not E cap. See, H is the operator. That's why you are putting cap here. But E is the observer, the quantity you want to know from this wave function. Suppose that this is a wave function, I am you operating it with something. Okay, to gain some information from this wave function which is relevant. Okay, so E, what we have got, E is the energy. This is not an operator. Okay, so from this Schrodinger equation, what you can observe is the energy which is corresponding to the system. From this psi, you can obtain this energy. So for all the three options, you cannot get all the information about the system, but from psi you can get the information of the system. And psi is known as wave function of the particle. Psi, which is a function of position and time. From these you can get all the information of the particle. Okay, so from psi you can get all the information of the particle. Actually, and you have seen the significance of psi. What is the significance? What is psi? Is it a real value, or it is a complex function, or what is this?
Sir, complex function.
Yes. So psi is not real. Psi, comma t. Some problems. Comma t. It is nothing but a complex. So actually, in one term, psi is a complex thing. So if you multiply psi with another psi star, its complex conjugate, you know when you are multiplying I with I, it will give I square, that is -1. That is a real number. Okay. So psi doesn't have any is a complex number. It doesn't tell that much, but if it is multiplied with its complex conjugate, you can get a real number. So is clear for all, or do you have any doubt? Anybody? Someone was trying to join actually. Let me join them. Yeah. So it's clear to everybody?
Yes, sir.
Okay. So I'm going to the next question. So this is the next question. Which of the following are necessarily the properties of a wave function psi, which is in bracket x comma t? Which of the following are necessary properties of a wave function psi x comma t? First is option is psi xt must have real values for all values of x and t. Second option, psi xt must be an eigenfunction of the Hamiltonian of the system. Psi xt must be independent of time for stationary states. Psi xt must have finite values for all values of x and t. So you can find this answer in lecture 2 also. There also it is mentioned. And so what will be the answer?
Sir, psi x comma t must be an eigenfunction of the Hamiltonian.
No. Anybody else? See, psi x comma t is the wave function, but it need not to be the Hamiltonian of the system, right? It could be any function. It doesn't need to be the Hamiltonian. Anybody else? Option 4. Who is saying this? Kayala Monica. Option 4. Okay. Yes. Option 4 is the correct answer. And this is the explanation. Whenever you have seen this, you have done this class, you have learned about that the wave function of a particle have some properties. What properties? These are the properties that the wave function must be normalized. Okay, that means if there is a wave function psi x comma t, if you are multiplying this psi with its complex conjugate that I have mentioned, if psi is a complex number, then if you are multiplying it with its complex conjugate, it will give you some number. Okay, so from minus infinity to plus infinity limit, if you are multiplying this psi with psi star xt, it will give you 1. So this is the main property of the wave function. Okay, and another property is the wave function and its derivative, that must be continuous and finite. Okay, so if psi, like let's say this psi x and del x psi. Okay, I'm just in this case. Okay, I will include time. Okay, excellent. X comma t. So these two, this first derivative and this function, this is continuous and finite. If there is some problem again. If you plot this psi against x, it cannot be, it is not possible, it will fall like this. This is not possible, it should be continuous. Okay, so these two properties is very important for wave function, acceptance of a wave function. How can I accept a wave function? Which wave function I can accept? For this, these conditions are necessary, that is, these must be normalized, and another is the wave function and its derivative, it must be continuous and also finite. Okay, for all values of x and t. Fine. Now why all other options, and I will explain now why about all other options. That first of all, first option is saying that the psi xt must be real values for all values of x and t. But I have explained that your psi is not a real value, it is a complex number. So first of all, this option is not possible. Okay. So the second option, one of you have told about this option, but what I have said, that the for acceptance of a wave function, it need not to be the Hamiltonian of the system. It could be anything. Just it has to satisfy these two conditions. On this basis, you can say that we can accept this psi as a wave function. Third point is psi x comma t must be independent of time for stationary states. So what do you know about stationary states? What is stationary state? Anybody can explain? What is a stationary state? When I can say state as a stationary state? Anybody? Try it. Just what do you know about stationary state? What is a stationary state? What do you mean by stationary? Some particle or something is stationary means what? Answer lies in this name, stationary.
Sir, at an instant of time or
Yes.
at a constant time?
Yes. Go on. I can't hear you.
Sir, when we define a certain wave function at a certain time or an instant of time?
Okay. Okay. So you are saying that when you are defining some function at a particular instant of time, that state is a stationary state. That's what you are saying, right?
Yes, sir.
Okay. So stationary state actually means that the state problem. A stationary state means a state which is not evolving with time. Stationary means something is stationary means it is not moving with time, or it is not changing with time. Okay, so it has no time dependency. Actually, this state has no time dependency. So this so at a particular instant of time t equal to 0, the state is what it should be at t equal to t or any time. Okay, but so we had what is the problem? Psi xt must be independent of time for stationary state. Yes, what I am saying that for stationary state the states are independent of time. So what is the problem here? Here actually the problem is that the psi will change. Psi also will change. Psi will not be psi. See, you can see that psi is a function of x and t. Okay, you can see here psi is a function of x and t. So with t psi will change. Okay, so and fourth option is the psi xt must have finite values for all real values of x and t. For here what is it written? That it is continuous and finite. The wave function, its first derivative, continuous and finite for all values of x and t. All values of x and t. Okay. So this is the correct answer. That psi xt must have finite values for all values of x and t. So do anybody have any doubt in this question? Anybody?
No, sir. No, sir.
Okay, fine. So I'm going to the next question. Okay, so third question is, one of the operators here given below is not linear. You have to identify that operator. Wait a minute, someone is trying to join. Oh, okay, yeah. Okay, so one of the operators here is not linear. The operators are a fx equals to x squared fx, a of fx equals to fx whole square, a of fx equals to del x of fx. It is x. You can, I don't know if you can see it or not. This is x. Okay, this is x, and a of fx equals to 0. So what will be the answer? Anybody? Anybody try it? First think about what is a linear operator. What a linear operator does to a function. Then you can get your answer. No answer? Okay, so you can find it in lecture number 2. So I am giving you some hint, and then let's see if you can answer this or not. Okay, so this is the definition of a linear operator. So operator is said to be linear if it follows the following condition. What is the condition? Suppose this is the operator A and this is a function, it is multiplied by some constant. This is another function which is multiplied by some constant, and whenever this operator operates, how it is operating? It is coming outside and it is just affecting on the functions. Okay, so a of afx plus b of gx, this is operated by an operator A. What is does? A is coming out, this A is thus involved with this fx, and B is also coming out, A is involved with the gx. So now can you answer which one of these is not linear? See, linear operator, what linear operator actually doing? You can see here. You can see here, just see these two. This is enough to answer. So whenever an operator is operating on this, suppose you forget about this one, okay? When it is operating on this A is coming out, it is going toward there. The function is not changing. Function is remaining the same, fx. So now you can you give me answer? I have given you some hint.
Sir, option C.
Option? Sorry, I couldn't hear you.
Sir, option C.
Option C. See here, this is means are not linear. Okay. That means here are three operators that are linear. One is there, it is not linear. You have to find that. But what who is saying this a of fx if del x of fx, right? So what I have said here, that when you are having an operator which is operating on a function and giving the function back is a linear operator, right? So here it is doing the same thing. It is operating on a function, it is giving back the same function. It is not a function, it is just operator. Okay, the operator is just this operator. So it is not changing the function. So it is a linear operator. And here question is mentioned that which one is not linear. Not linear. So C could not be possible. Anybody else? Anybody? No response. Okay, fine. So first I am showing the correct answer. Yes, this one. The second one is not a linear operator. How? Because what I have explained you that a of fx, first of all I am taking the first one. This is x square f of x, right? A of fx. This again I am saying, please ignore my drawing, just understand the concept. This a of fx is x square into fx. So when it is operating, it is giving the function back with some constant, something is multiplied with it. Okay, so it is a linear operator. But when you are operating this with this and giving you f of x, sorry, but when you are using this one, This is changing the function completely. Okay, your initial function was fx, and it's changing your function completely. This is fx square. This is a different function. Okay, so it is not following the condition for not, it is not linear. Okay, now the third one I have explained why it is not a linear operator, because here is the explanation. You can see that it is giving the same function in back. And what about the fourth one? Why this is not linear? Why this is linear? A of fx is 0. Anybody? It is not giving the function back. So how is it linear? Why I am not saying that it is not linear? Anybody? Try it. Anybody? I am repeating the question again, that where I am saying that operator is said to be linear if it is operating on the total on a function, and if it is multiplied by some constant, it will operate on that function. This constant is coming out. And then in these three cases you have seen the case for the case of this one, sorry, for the case of this one, it is getting the function back, another multiplied by some another function. Okay, so and in this case you have seen also the function is there intact. Okay, it is directly operating on the function, and here in this case their function is it is getting squared. This function is not back, it is getting squared. Okay, so this operator cannot be a linear operator. But for in case of a of fx, I can draw, I am writing it cleanly, so that everybody can answer it. I have saved it, sorry. So a of fx equals to 0. Here what I have said, that function will come back, function is not coming back. So how is this not a linear operator? How this is a linear operator? I am saying it as a linear operator. How? Why? Am I wrong, or is there any reason? Anybody? Anybody? Okay, fine. No answer again. So a of fx is equals to 0, and you know that if you can multiply something with 0, it will give you 0. So you can write this 0 as 0 into fx. So your fx function is there, but since your the value which the operator gets from it is 0, then it is the linear operator, because it is giving back the operator, it is giving back the function again. So in these four options, we have among these four options, the option 2 is that a of fx equals to f of x square. This is not a linear operator. So are you satisfied, and anybody have any question? Please ask me any question. If there is any question, you can ask me. Everybody is gone or what? I'm getting no responses. Oh. So everybody is clear, or I repeat once? What? Okay, fine. Since nobody is giving me that any answer, so I'm moving forward. So this is the fourth question. For a particle in 1D box where the particle is confined between x equals to 0 and x equals to a, if the particle is in the ground state, that is the lowest energy state, you know the ground state is the lowest energy state of a particle, and the upper states are called excited states. Okay, so which of the following statement is not correct? See the question where it is written not correct. Okay, so whenever I will ask you the answer, don't tell me the correct one. Okay, so tell me the not incorrect one. So what is it saying? That if there is a particle in a box, 1D particle in a 1D box, you can see it in the lecture 4, that particle in a 1D box, and this length is 0 to a. Okay, that is what it is saying, that this is the x-axis, the x-axis. Okay, it is in the ground state. Which of the statement is not correct? That first question option is wave function does not depend on time. The wave function, that is here psi, it does not depend on time. Is this the correct thing or not? The second one, the wave function is 0 at x equals to 0 and x equals to a. The third question, the third option, the probability density does not depend on time. And fourth option is the probability density is 0 at x equals to 0 and x equals to a. So what will be the answer? Kayala, Monica, yeah, option 1. Okay, anybody else? Okay, Monica, so why do you think that option 1 is correct? Correct means, I mean, in this perspective, but is incorrect. Why? Yeah, wave function. Oh, yes. I think I have mentioned it, that the wave function is a function of what and what? Position and time. Psi is a function of x comma t. Yes. So wave function will always depend on time. Fine. But why others are not correct? or why others are correct here. In this question, all these three are correct. These three are correct. This one is correct, but this is not correct. Why? So this is a brief explanation that you have seen this in lecture 4. Whenever particle in a box was there it was mentioned that for a particle in a box which is confined in a box of length a, this is the definition of this wave function, this psi x comma t, which is equals to 2a by a whole to the power 1 by 2 sine n pi x by a into e to the power minus I en t by h cross, and this is the value of energy for this particle in a 1D box. This energy is n square h square by 8 m square. Okay, and you can see in this wave function there is a part which involves time. There is a time. Okay, so their wave function, it depends upon time. So why other options are correct in the that wave function is 0 at x equals to 0 and x equals to a. So I am going to discuss about topic. So x equals to 0 and x equals to a. See, when particle in a box was solved, Professor Hajra has solved this particle in a box. He has shown that this proper particle in a box, there is some boundary of condition of some problem with this board. Boundary conditions. What is the boundary conditions? That psi x is 0 for x equals to 0 for x equals to 0 and x equals to a. That is, here psi value is 0, here psi value is 0. Because outside, what particle in a box says that if we to restrict the particle to move in the box, the outside potential is infinite. Okay, so since outside potential is infinite, so particle cannot go out of the box, it is just moving inside the box. Okay, and the boundary condition is that this psi, this wave function of the particle, is 0 at this x equal to 0 and x equals to a. So this is the correct one. So you can see the wave function is 0 at x equals to 0 and x equals to a. This is the correct one. What I have said, this is the correct thing. Okay, so the probability density does not depend on time. Fine. So what is the probability density? Do you know the formula? What is the probability density formula? How do you know the probability density? Say me. Anybody?
Sir, psi x square.
Psi x square, right? So in better way you can say this as psi x star psi x. Psi x star to psi x. Okay, this is the probability density. So you can see if suppose just sorry. So here time is involved, so I have to involve this time also. So psi star x comma t into psi x comma t. So here I am getting just psi to clarify it easily, but you can see if when particle in a box in 1D box was solved, that this time part was multiplied later. Okay, but for probability density calculation, I am showing this one, this psi star x comma t into psi x comma t. Okay, so I am just briefly explaining why this does not depend on time. I am saying that it is written correctly. The probability density does not depend on time. How? Because you can see here in the wave function, this e to the power term has minus I ent by h cross. And what it happened that if you are taking psi star, what will be the psi star? The psi star will be, oh, I read somewhere else. So, sorry, 1 second. So here I am writing psi star x comma t. See, what is psi star? Complex conjugate. I have said psi and psi star are complex conjugates. So if it is 1 plus I, it will be 1 minus I. Just the I thing will change. The complex conjugate will, the complex part will change just. Okay. So this first term, there is no complex thing. 2 by a to the power 1 by 2 sine n pi x by a. There is no complex part. Okay. So I am just not writing this whole thing. I am just writing it as some constant c into e to the power, what will be the complex conjugate of minus int by h cross? This will be plus I en of ent by h cross. Fine. So c, what is c? C is nothing but this one, 2 by a to the power half sine n pi x by a. So for clarification, I am writing this c as this 2 by a to the power half sine n pi x by a. Okay, so anyway, I have written that. So I am using c. Okay, so I have, so c is some nothing but it is not changing with psi and psi star. Whenever I am taking the complex conjugate, this real part is not changing, this imaginary part is changing. Okay, so when you are discussing probability density, so what will be the density formula? Psi star into psi. So psi star into psi is equals to, so psi, what is psi in terms of c? Psi in terms of c will be c psi x comma t, it will be c of, I don't want any figure. This psi x comma t will be c e to the power minus I e n t by h cross. Fine. So psi x comma t will be c into minus e to the power minus I e n t by h cross, and psi star will be c into e to the power plus I e n t by h cross. Okay. So whenever I am doing probability density calculation, psi star into psi, you can see this 2c c into, okay, I am going step by step. For psi star it will be plus I e n t by h cross into c into e to the power minus int by h cross. Fine. So you can see these two terms will be multiplied. Okay, this will give me c square into, and these two will be e to the power plus int by h cross into e to the power minus int by h cross. So e to the power a into e to the power b, you know, it is written as e to the power a plus b. Everybody, you know, every one of you is understand that int by h cross minus, okay, I am writing in elsewhere, this is too much congested. C square into e to the power plus I E N T by h cross minus I E N I E N T by h cross. Okay, so it will be 0, this will 2 plus minus, so c square into e to the power 0, and you know e to the power 0 is nothing but 1, so it is c square. Okay, so it is nothing but c square. So what is c? I have mentioned c is nothing but 2 by a whole to the power half sine n pi x by a. Okay, so c square means this is the square, just 2 by a into sine square n pi x by a. 2 by a whole to the power half, this will be squared up, so it will be 2 by a, just not the root over 1, and this sine n pi x by a will be sine square n pi x by a, but there will be no t term, it will be what IET by h cross term in the probability density. That's why they have mentioned that the probability density does not depend on time, and this is the correct one. Okay, and the fourth point they have mentioned that the probability density is 0 at x equals to 0 and x equals to a. So at x equals to 0, I have mentioned that this wave function is 0 at x equals to 0, and at the same thing is at x equals to a, that is the wave function is 0. So whenever you are multiplying to 0, it will get 0. So the probability density is 0, because probability density is nothing but psi star into psi. So psi is, if psi is 0, psi star is also 0. So if you multiply psi and psi star, this you will give 0 into 0, which is 0. So probability density is 0. So the correct option is which one? Correct option is the wave function does not depend on time. Which one? This one. Yes. The wave function does not depend on time. This is the correct answer. So do anybody have any confusion in this question?
No, sir.
Okay, you have understood clearly?
Yes, sir.
Okay, fine. So I'm going to the next question. For a particle which is confined in a 1D box, same question, just particle is confined in a 1D box between x equals to 0 and x equals to a. If the particle is in the stationary state, which corresponds to n equals to 2, then its average position. What will be its average position? Okay, so I am just drawing it again, that this is the x-axis, particle is confined here, this is x equals to 0, this is x equals to a, particle is moving here. So in this 1D box, if it is in a stationary state, which is corresponds to n equals to 2, so what will be its average position? Okay, so first of all, the option is it has a probability distribution with a peak at x equals to y by 2, probability distribution with a peak at a by 2 is at a by 2, x equals to a by 2 is at x equals to a by 4 and x equals to 3 by 4, and differs from what it would be possible if the particle, what it would be if the particle were in the stationary state corresponds to n equals to 1. So you can find the answer in lecture 4. So before moving to the solution, I would like to ask anybody if anybody can answer this. Yes. Hello. Someone's microphone is on. Ramadev Vedu, please, can you please mute yourself?
Yeah, yeah, yeah. So the
Yes, yes. On.
third answer, that is x equal to a by 4 and 3, a by 4 is correct answer, sir.
X equals to a by 4 and x equals to 3 by 4.
Yeah.
Okay. I will take a one or two more answers, then I will explain. Any other anyone else? Anybody else? Okay, fine. So this is the explanation. The average position of a particle is actually described by this equation. To describe the average position of a particle, this is the explanation. This is the explanation. That average x is defined as psi of x comma t, and you have seen this direct bracket notation. This is the bra and this is the bracket notation. This is psi x comma t, x psi x comma t, and upon putting the value of x is I, you can see that whatever is the value of average x, which is becoming just a by 2. I am now showing it to you. Okay. And this a by 2, whenever it is coming at average x is coming to be a by 2, there is no n term. Okay. So if since there is no n term, so whatever be the n equal to 1, equal to 2, n equal to 3, the average position is the same. Okay, average position is the same. Particles average position is the same. Don't confuse with the probability, this plot for this probability. Okay, so average position, particles average position is the same at x equals a by 2. So how this is coming, I will explain you mathematically. Okay, so can anybody help me with the wave function for particle in a box? Okay, so it seems no one wants to help me. Okay, let me write myself. 2 by a whole to the power half sine n pi x by a into e to the power minus I n t by h cross. This is the wave function for a particle in a box, right? Now whatever I say to know the value of average x, so it is the 0 to a integration. Okay, so in bracket notation what you should write is psi x comma t x t. Okay, so just remember one thing, whenever you are going to write any Dirac notation or in bracket notation, you should not write this star. Okay, this first one, this first term, this implies that this is the complex conjugate which is there. Okay, to remove this complex conjugate one, this bracket notation was used. In bracket notation there is no star. Okay, so just in terms of integration I will write an integration from 0 to a, there will be psi x comma t. So first term will be psi star x comma t into x into psi x comma t into dx. In integration, you know, last in the last side there is dx always. Okay, so you can see here. Oh, sorry. Okay, yeah. You can see the psi and psi star. I have explained in the previous question that for psi star, what is the change? What will be change? Actually, this e to the power I minus I n t by h cross, it will be replaced by e to the power plus I e n t by h cross. Nothing will be changed. The front line, this 2 by a into the power half sin n pi x by a, this part is not changed from on going from psi to psi star, but there is a change of this e to the power minus I n t by h cross term. Okay, so I am writing it as 2 by a whole to the power half sin n by x by a into x. I am just writing. Okay, first let me write and then I will explain why I am writing in this way. Okay, fine. So I am just, what I have done, I have just separated these two part. X was there, x was already there. I have just taken this term separately, this x term and this is t term. You can separate it. This is the x term which contains x and this is the t term which contains information about the time. Okay, I have separated the x terms from these two psi star and psi, and I have taken this x and also, and on the, so in the second part what I have done, I have separated the time parts. Okay, so this is general practice. This is done always in mathematics or physics. You have also done that. Just 1 minute. No one thought there was a message. Okay, it's fine. You can see here, so 2 by a to the power half into 2 by a to the power half. What will be? What we will get? We will get 2 by a. There will be no half because 2 halves will multiply. This will be 2 by a into x. This x is coming over here, and there is two sine terms, sine, n pi x by a. Fine. Now what about the e to the power terms? You can see here there is plus int by h cross and there is minus int by h cross. So these will cancel out each other. So there will be no t term. Oh sorry, I forgotten to write dx here. So there was a dx also. So I am writing it over here, dx. Okay. So it's dx. Fine. So this is my expression now. 0 to a, 2 by a x sine n pi x by a into dx. Sorry, there will be sine square. Because two times sine functions are there. Sine square n pi x by a dx. Now I am removing the constant part. There is no x in this one. Okay, so I am removing that. So what we left with? X sine square n pi x by a dx. Good. So far so good. Now we have to do this integration. And then we will find what is the value of this average position, because you are just performing this calculation to know about the average position of the particle. So I am moving to this side. So my intention is to find this integral 0 to a x sine square n pi x by a to dx. Obviously dx. So I will find out this value here and then I will put it here. Then I will get the value of average x. So equals to, so you know this formula that 2 sine square x can be written as 1 minus, sorry, cos 2x, this can be written as 1 minus 2 sine square. Every one of you know the formula. This is a trigonometric formula. This cos 2x equals to 1 minus sine 2 sine square x. It's good if I write it. Problem is happening. So I am just replacing here. So how will you replace? So how are you going to replace it? You have just sine square, okay? So you have for the sine square x, so what will be the value of this sine square x? Sine square x would be, what would be the sine square x? 1 minus cos 2x, 1 minus cos 2x. Okay, so to know about sine square x, you are just pushing this one to on the opposite side of this equal sign, and you are getting, this is dividing by 2 because there is a 2 here. So you are getting sine square x is half of 1 minus cos 2x. So x into half of 1 minus cos 2x. X is not here, So it is n pi x by a. Here this is my x here. Okay. So I am again removing the half outside, 0 to a, 1 by x minus x cos 2n pi x dx. Okay. Now you can see there is two terms and there is a negative sign, so I can separate this integral. I can giving 1 by 2 outside. My first integral will be 0 to a x dx, and second integral will be half is outside, so I am not worried about half. This is x cos 2n pi x by a. That is dx. Good. Equals to, so you can see here what is the integration of x dx. X dx
X
is
square.
exactly x square by 2. X square by 2. I'm just writing the limits here, 0 and a, and this is going to be solved using integration by parts. Everybody knows about integration by parts, that when you have two functions, I'm writing the formula here, integration by parts, that if you have some integration of u into v d u of x of vx into dx, then there is the formula is that if u is, I considered u as the first function and v as the second function, so my formula will be u integration of v dx minus, there's a huge minus, minus integration d dx, another problem, I'm writing it below so that, oh sorry, okay, you can see here u into v dx, and write it as integration, sorry, and so much mistakes, u integration of v dx first function integration of second function minus integration, there is a differentiation of the first function d dx of u, again integration of v dx. Okay, so this is the formula for integration by parts. You have learned in math in class 12 mathematics. Okay, so this is the first, if u is the first function and v is the second function, then when you are they are multiplied, when you are going to integrate that, the formula will be like this. Okay, so now and among these there is a sequence that which function we will take as the first function and which one as the second function. This x will be taken as the first function. This is, there is a rule you can you remember about this ILATE rule, that inverse trigonometric, inverse logarithmic, algebraic, trigonometric, and then exponential. Okay, so algebraic function, since algebraic this is an algebraic function and it is a trigonometric function, so it will be the first, it will be the second. So I'm just writing this in terms of integration by parts. That is x integration cos 2n pi x by a dx minus, I'm going below, minus again integration ddx of first function, right? So what is my first function? X. And what is the ddx of x? It's 1, right? So I'm not writing it again. So there is double integration for phi dx. Liquid is 0 to a. Sorry, phi d, no, here not b. There is this, what will be there? It's cos 2n pi x by a. Good. Okay. So this is the this is what we have got. You can understand why there is double integration sign. This integration sign comes from this integration actually coming from this one. You can see here this one. Okay. And this since x is the first function, when you are differentiating with x, this is giving you 1. So there is double differentiation. Okay, so half again, if we are putting the values of a, x square by 2 as a and 0, it will be a square by 2 minus 0 square by 2, that is 0. It's basic. Minus x and integration of cos 2n pi x by a. Okay. So it will be, what is the integration of cos?
Sin x.
Sin x, and if there is something cos ax kind of thing, then
Sir, we have to divide it by.
divide by a, right?
Yes, sir.
Yes. There will be sin, and if it is positive or negative?
Positive, sir.
Are you sure?
Yes, sir.
Yes, it's positive. Okay. So this is the integration of cos 2 pi nx by a. This is sin n 2n pi x by a divided by 2n pi by a. Good. And what will be the limits? Limits will be 0 to a. Okay. And so, and what about the second one? Just imagine we are integrating this cos 2n pi x by a twice. So in first one, cos is will give you sine. Okay. And when you are differentiating, so when you are integrating this sine again, it will give you cos, right? So you will get finally, after double integration, your product will be cos 2n pi x by a, cos 2n pi x by a divided by this 2n pi by a whole square. And there will also be a change, because whenever you are changing this cos to sine, then there is no change in the symbol. Cos to sine integration is positive, what you have said. But if you are getting again, it is you are integrating, then the sine will be converted to cos. But conversion of sine to cos is negative. Sin x equal integration of sin x is nothing but minus of cos x. So this minus will make it plus. So what will be its limit? It's 0 to a. So it's very congested, that's why I will take another slide, and then I will come back here again. check once. Yeah, it's recording is on. Okay. So here I can write it. That's psi. Oh no, psi. This what was the value? This integration was 0 to a x sine square n pi x by a. Okay. Integration 0 to a x sine square n pi x by a. This is the one. Okay. So what we have got, I have to check that. Sorry. 1 by 2, there was a square by 2 minus x sine 2x 2n pi x by a sine 2n pi x by a divided by 2n pi by a, and this has a limit of 0 to a, then plus cos 2n pi x by a, should put it in the bracket just like the sine one, and it will be divided by 2n pi by a, and that is the whole square. And it has also limit of 0 to a. This is my perfect close. Okay. So this half square by 2 minus, if I put sine in x equals to a, so my expression will be, I will write it as a sine a 2n pi into a by a will cancel out, so there will be 2n pi divided by 2n pi by a. If I put 0, this will be 0, so 0 has no significance here. Okay, for x equals to 0, I am not going to the sine one, because if x equals to 0, then all will be 0. This whole term will be 0. So the significant term is a sine. I am putting x equals to a. This a is cancelled out, so I am getting this one point. Okay. Then, so 0 to a, this is done, plus, when I am putting a, x equals to a, what is the first term? This is cos 2n pi. The same just like the sine one. Okay, this x equals to a, this a will cancel out. And what if I put x equal to 0? This will be cos 0 divided by same term 2n pi by a whole square. Okay. Okay. Now be careful. This is square by 2 I am writing minus. You can see sine 2n pi. So whatever be the value of n, 1, 2, 3, 4, it could be anything. When you are multiplying by a 2, you cannot get you cannot get a odd number. You cannot get never a odd number. Okay. So if you are multiplying something by 2, it must be a even number. Now there is the multiple of pi with even number. Sine pi, sine 2 pi, sine 4 pi, sine 6 pi, sine 8 pi. If you can go, this is 2 pi. It's complete circle. Okay. If I Okay, let me draw there. Okay, so sine 2n pi. Suppose this is my 0. Okay, so I am moving. This is pi. This is 2 pi. Where I am coming in the basic initial stage. Sine 4 pi. Again 2 pi. This is I am coming to the same stage. So what's the value of sine 0? Is the value of sine 2 pi, 2n pi. And what is sine 0? This is 0. So this whole term is nothing but 0. Okay, it's clear. Next I am coming to this cos term, cos 2n pi. What about cos 2n pi? Similarly, it will be the even multiple of cos, not its odd multiple is not possible. So similarly, for just like the sine function, the cos function will be multiplied by an even multiple of pi, just like cos 2 pi, cos 4 pi, and just like what you have seen, this cos just like in sine 2 pi, sine 4 pi, even pi is just like sine 0. And similarly, the cos 2 pi will be cos 2n pi or cos even multiple of pi will be just like the cos 0. Cos 0 divided by, or cos 0, you can write its value, it's nothing but 1. Okay, right? You know cos 0 is 1 by 2n pi by a whole square, minus here cos 0 is 1, 2n pi by a whole square. Okay, so plus and minus, this will cancel out. So what we are getting, this is getting just a square by 4. Okay, this is our final value of this one, of this integral. We are getting the value a square by 4. Now we are coming to the previous case. In this case, the value was 2 by a into, and you are getting this value as a square by 4. So if it will cancel out, so we will get a by 2. This average x will be a by 2. So I have proved that the average position of the particle is a by 2. And you can see here that there is no n term. It is devoid of any n. Whatever be the n quantum number n, the particle average position is always a by 2. So in the main question, this is the correct option, that particle is always at x equals to a by 2. This is not possible, I have shown you. And probability distribution has no peak, but the distribution yes has a peak, but this is not the correct here, because it's it's actually asking about the average position. So this is the correct one, and it does not differ from where it is if it is in the n equal to 1 state, because it is the same one, because and it is independent of n. Whatever be the n, it is 1 2 3 4, this average position is constant. So are you convinced, everybody? Any question?
No, sir.
Okay, you have understand that?
Yes, sir.
Okay. Okay. So I am moving to the next question. Very less time left today. So which one of the following is Einstein coefficient is not possible? So very basic term, I would like to say Einstein coefficient is E1. This is an energy level E2. Number of particles here is N1. Number of particles here is N2. Okay. So three processes are possible. As I have mentioned in the very first slide, there could be absorption, there could be emission, and another type of emission is also possible. This is stimulated emission. You can see this reference in lecture number 5, and their Einstein coefficients are A21. Sorry, getting it wrong. So A21 is the for spontaneous emission. Suppose this is my A21. B12 is my absorption and this B21 is my stimulated emission. Okay, so for you guys to remember, there is maybe a confusion between these absorption coefficients. What is the values of these absorption coefficients? There may be some misconceptions, but you can remember it easily that, see, in case of stimulated emission and absorption, one thing is common, that you need light. These processes cannot happen without light. Okay, but spontaneous emission, once you are excited, we have excited a molecule to the excited state, it is coming down to the ground state spontaneously. So it does not depend on light. Fine. So absorption, since these two processes, stimulated emission and absorption, these are controlled by light, so these two coefficients are related with B coefficients. Okay, and since spontaneous emission does not depend on light, so it is A coefficient. You can think this in this way, and these suffixes, this 2 1 1 2, you can clearly make a statement that this transition from one state to another, this is the transition from these two ones symbolize transition from 2 to 1, because it is a spontaneous emission, it's coming from excited to the ground state, so it is transition from 2 state to 1 state. Similarly, for stimulated emission, this 2 1 signifies the transition from 2 state to 1 state. Since similarly, absorption from 1 to B12, that means from 1 state to 2 state, first state to excited state. So this is absorption. Now my question is here, which of the following is not possible? You can see here A21 is there, which stands for, I'm sorry, S21 is there, which stands for spontaneous emission. B21 is there, B21 is there for stimulated emission, B12 is there for absorption. So my correct answer will be A12. There is no Einstein coefficient regarding A12, because you can clearly think of that what I've said there. If you can, if there is A12 kind of thing, that means if what I have said in Einstein coefficient A, there is no light. You don't need light. It is happening spontaneously. So you are just exciting a molecule from state 1 to state 2, from state 1 to state 2 spontaneously without the presence of the light. You don't need light to excite a molecule. This molecule are exciting spontaneously. This doesn't happen. Okay, you need some light to excite the molecule, so this is not possible, and so the correct answer is A12. Everybody fine?
Yes, sir.
Okay. So again a question is coming about which of the following relations are correct. B12 is equals to B21, B12 equal to A21, A21 equals to 8 pi h nu 12 whole cube by c cube into B21, and B21 is equals to 8 pi h nu 12 cube by c cube into A21. So what could be the answer? You can find it in lecture number 5. What could be the answer? Try it, anybody? Anybody try? Okay. So this is the answer. That from Einstein coefficient, following relations are established. Einstein gave these relations, that is B12 is equals to B21, which is a common B. That's why it is called A coefficient, because A is only one in number, A21, and these two B's are equal, so A and B coefficient. This is called Einstein A and B coefficient. That's why. Okay, so I am drawing the same diagram like the previous. Okay, so let me go to the, so you have got this answer, that B12 is equals to B21, these two relations, that the Einstein. This is the straightforward answer, but how these are coming? My question is how these are coming. So I'll now explain that in a very short way. Sorry, E1, this is excited state E2, Suppose there are n1 number of particles, suppose there are n2 number of particles. Now this is some process, absorption, this is emission, these two types of emissions are there. So I am naming it as B12. So what will be the spontaneous emission? What will be the symbol? A or B? What will be the symbol for spontaneous emission, A or B? No answer. Okay. This is A as I have discussed, and this is coming from 2, 1. Similarly, this is stimulated emission. This is from 2 to 1. So it is naming as B21. Fine. Now you have, all of you have read kinetics, chemical kinetics, right? So if I am writing that number of particles in the ground state that is getting decreased with time, this is minus d1 by dt, because this is getting decreased with time. The number of particles at the ground state is decreased with time. So I can write it in terms that it is, since it is involved with this process, this is B12 into this rho nu into n1. Okay, I can write it. And now what is rho nu? You have seen Professor Sayan Bakshi has explained this. Rho nu is nothing but, it is getting from Planck constant, h by 8 by h nu 1 2 whole cube by c cube into 1 by exponential h nu by kt minus 1. This is coming from Planck's black body radiation formula. This is the radiant energy density. You have heard the term in this lecture, that radiant energy density, and this is the radiant energy density. Okay. Correcting it. Okay. Yeah. So this is, since this process that in population decrease in the n1 is due to absorption, and this is happening in presence of light. So this light rho is involved. This rho nu is involved here. Similarly, the loss of population of the excited state can be defined as two processes. This is A21, which is devoid of any light, just n2 particles are there, because in spontaneous emission there is no involvement of light, but for stimulated emission there is a rho nu factor and multiplied by n2. Okay. Now under equilibrium condition, when dn1 by dt is equals to dn2 by dt, we can write this B12 into rho nu into n1, can write it as A21 into plus B21 rho nu into n2. Okay, these two terms you can write. Just I am writing just this dn1 by dt, the rate of decrease of number of particles in the ground state is equals to increase in the decrease in the number of particles in the ground state, and this is equals to the decrease in the particle in the excited state. Just I am matching this dn1 by dt is equals to dn2 by dt. Okay, so this is the equation. Now I want to derive, I want this rho nu. What will be the rho nu? To rho nu, so this term will come this side, this one, this two, B21 rho nu into N2. So what will be left? Initially it was B12 into N1 minus B21 into N2 equals to A21 into N2, right? This one term is left there. just this term is coming to the left hand side, and I am taking this common. Okay, so what will be my rho nu? My rho nu will be A21 N2 divided by B12 N1 minus B21 N2. Good? That's so far so good. Okay, so I'm moving to this side. So rho nu is nothing but A21 N2 which is divided by B12 N1 minus B21 N2. Okay, now what I'm going to do, I am just dividing up and down with the term this B1 N2. Okay, so what I am doing, you will understand after some time. Sorry guys. Problem. Okay, so leave it. A21 divided by B21 divided by B12 divided by B21 into what I am getting, N1 by N2, right, minus 1. Because I am dividing by this factor, the upper one, this N2 will cancel. If I am dividing by A21 N2 by B21 N2, there will be A21 by B21 which is left in the upper side, and in the denominator there will be B12 by B21 into N1 by N2. Is someone trying to say something? Okay, this one fine. Now you know the Boltzmann distribution. What is the Boltzmann distribution? What does it say? It says that N1 is equals to N0 into, sorry, just change it. Yeah, so N1 is equals to N0 e to the power e minus E1 by kBt. Similarly, what is N2? N2 is just the same way. N2 is N0 e to the power minus E2 by kBt. So if you know about Boltzmann distribution, it's okay. If you don't know about Boltzmann distribution, whenever you will do statistical mechanics course, then you will understand what is the Boltzmann distribution. Okay. So now whenever I am what I need N1 by N2, right? So I am doing it N1 divided by N2. So what will be the answer? N1 by N2, N0 will be cancelled out, right? Because N0 into e to the power minus E1 by kBt divided by N0 e to the power minus E2 by kBt. So N0 will be cancelled out. So what will be left with? This e to the power minus E1. This E2 will be in the denominator because N2 is the denominator. Okay, so this E2 will go up and it will be plus by kBt. Okay, everybody understand that? That whenever there is e to the power minus E2 by kBt in the denominator, when it is going to the numerator, numerator, then it will be getting its sign change and it is getting plus. Okay, so I am taking negative common, so e to the power minus E2 minus E1 divided by kBt. Okay, this is e to the power E2 minus E1 by kBt. This is nothing but what? My N1 by N2. Now you have known the condition that for a successful transition there will be condition that E2 minus E1 will be h nu, the energy of the photon, h nu. E2 minus h nu, E2 minus E1 should be equal. So much problem in this code today. So E2 minus E1 is equals to h nu. This is the condition. Okay, this condition is satisfied if then this transition is allowed. Okay, so E2 minus E1, so I can replace it with E2 minus E1 and we will get h nu by kBt. Fine. So this is my value of N1 by N2. Okay, so I am just replacing here. So what will we get? A21 by B21 into, I am writing in this way. Why I am writing, I will explain then. So this will be 1 divided by, and N1 by N2 will be replaced by e to the power h nu by kBt minus 1, and there will be as a term B12 by B21. Okay, so there will be minus, or I have missed it also, here also will be minus. Okay, now you see this equation row of nu, this is A21 by B21 into this one. So I can see that if you are comparing this with the Planck's equation, you can see to satisfy this Planck equation you need this term B12 by B21, it need to be equals to 1, right? To satisfy this Planck equation which is written above here, you can see these two equations. Okay, okay, now see this B12 by B21 needs to be 1 to satisfy this equation, and another one will be what? This A21 by B21, this must be equals to this factor, right? Then in that case you can compare these two. So what will be the conditions? Then A1 condition number 1 will be B12 is equals to so B12 divided by B21 is equals to 1, which implies what? That B12 must be equals to B21 equals to B21. Okay, so B12 will be equals to B21. Fine. And what will be the other? Other will be, I am writing in the, okay, there's, yeah, there is some space. Write it here, that A21 divided by B21, it must be equals to, what will be? 8 by h nu cube 12 by c. If you just put b there, so it will be A21 equals to this factor 8 by h nu cube by c cube into B21. Okay, so you are getting these two relations from this Einstein equation, and Einstein gave those relations, and this is your question, that what two relations will be there. I have explained B12 is equals to B21, and this is known as B, and another will be A21 is equals to 8 by h nu cube 12 cube by c cube into B21. Everybody understand that?
Yes, sir.
Okay, fine. The next question is a very straightforward question. That correct like property and corresponding phenomena, which one is matching with what? Fine. So first of one is the two effects are there. First one is Compton effect, another is interference. Let me see, someone is trying to again enter. Okay, fine. It's there. Okay, so Compton effect, you can find this question and answer in the lecture number 1. There is two effects here, Compton effect and interference. So I'm just explaining what is Compton effect. Compton effect is just Compton does this experiment to whenever there was two schools of thought, one thought light as a particle, another thought light as a wave. Compton breaks these. Compton proved that light is a particle. How did it proved? He used X-ray for low energy, high energy X-ray, and when it is scattered by some electron, it is actually there is a low energy X-ray photon is scattered. That means energy of the photon is decreased. So photon is whenever you are purging, whenever the photon is interacting with the electron, it is losing some of its energy to this electron, and it is scattering with an energy lower than the incident energy. Okay, so this is only possible if this light is a particle. One particle who interacting with another particle, and then you can transfer this energy. So this Compton effect proved that light is a particle, or in some cases you can see matter or something. Okay, here in this case there is matter or particle. So which options could be possible? This one, wave Compton wave effect particle and Compton effect particle. These two are there. In these two options this particle is there, this particle. Okay, and so what is interference? So interference is that interaction of multiple waves under certain conditions, and so what I have explained, that to prove the wave nature of light, one experiment was done, which is interference. When two waves are coming, then when they are when they actually falls on each other, there would be in some point they cancel each other, and in some point they reinforce each other. Okay, so what happens that you can see here, this wave, this maxima is matching with this maxima, and so this is getting amplified. This maxima is getting amplified. Okay, but when this maxima is matching with this minima, this is getting decreased. Okay, so this is called constructive interference, and this is called destructive interference. You have learned that in physics also. So this what is the conclusion, that it proves that light is a wave. When two waves actually combine, then this phenomenon is happening. There happens that some point it could be constructive interference, or it could be destructive interference. So what will be the right answer? The right answer will be Compton effect related to particle, and interference is related to wave. Okay, everybody?
Yes, sir.
Okay, fine. Okay, now very easy question for everybody. Wave has a frequency of 10 hertz and speed of 50 meter per second. So what will be the corresponding wavelength in meter? Can anybody do it quickly? What will be the answer? Anybody? You have given a frequency, right? And the speed of light is 50 meter per second. So what is the relation between speed of a wave and frequency? Very common relation. Anybody? Okay, so I'm giving some hint and then you can answer. Oh, I have done this answer. So your frequency is nu is 10 hertz, or it can be expressed as 10 cycles per second or 10 second inverse. Okay, second inverse, and it is your V, that is 50 meter per second. So whenever you are, it is the relation between wavelength and wavelength and frequency, that when you are multiplying these two, sorry, could be, this could be confusing with the nu and v. So this is nu into lambda, this is equals to v. Okay, v is the speed of the wave. Speed of the wave is p. Okay, so you have given this value of nu. Nu is 50 meter per second. And what is lambda? Lambda you need to find. And what is v? V is, so sorry, I'm getting it wrong. Nu is the frequency, it is 10 hertz or 10 second inverse. And what is v? V is velocity, is 50 meter per second. So what will be lambda? Lambda will be v by nu. So what is v? This is 50 meter second inverse by 10 second inverse. Whenever you are going to do mathematics in physical chemistry, you must always careful about unit. So this second inverse will be cancelled out. 10 and 5 will be 5 meter. So the lambda will be 5 meter. You have got this answer. Okay, fine for everybody.
Yes, sir.
Okay, fine. So I am going to the last question, that color and number of lines of sodium in atomic absorption spectroscopy is what? So
Yellow 2.
Sorry?
Sir, option B, yellow.
Yellow and 2. Okay, very good. Very good. This is the option. Now, for this, you can find in so those who don't know this answer, this you can find it in reference in lecture number 1. So I am just explaining in very briefly that whenever solar spectrums, Newton explained the solar spectrum, he found some lines which he explained as his Fraunhofer line. There was some dark lines, and in this dark line he did not know what is this coming from. But when he used the spectrum of sodium, so whenever you have done, some of you have done flame test, right? So also Professor Bakshi has said that in flame test, you can see when you have a salt of sodium chloride, you are putting it in the flame, you can see bright yellow color. Okay, so this bright yellow color, whenever you pass it to a prism, you can see in this emission spectra these two closely spaced line. Okay, so these two closely spaced line matches with this line. That's why this is called D, sodium D light. Okay, in whenever we'll do this polarizer experiment, so you can see here that in polarizer sodium D lamp is used. So you don't be confused with this D, because this is the D, this is the D line, this is matching, and these two lines are very closely spaced. So what is the origin of this line in atomic absorption spectroscopy? So this, you can see this is because due to the transition from 3p to 3s level. Just shortly explaining this, 3ap 3s. So do anybody know why there is two levels but you are getting double line? So since two levels you can get only one line, you are getting two lines. Why? Anybody? Try it. Why you can see that here, you know, the sodium last cell is 3s, right? If you write the electronic configuration of sodium, the last cell is 3s1. So there will be two states. Here is 3s, there is 3p. Okay, so only one line is expected. So how can you getting the double line? Quickly, anybody? Okay. So have you heard about term symbol? How many of you have heard about term symbol? Atomic term symbol. I am talking about atomic term symbol. How many of you have heard about atomic term symbol? Nobody? Okay. So I'll explain. It's very short. Term symbol is calculated. Yeah. So term symbol is calculated. Suppose I have a configuration of 3s1. I have to know two things. First, you have heard about this quantum number, principal quantum number, azimuthal quantum numbers. Have you heard
Yes,
about
sir.
that? Yes. Okay. So if so, how did you express this azimuthal quantum number? By L, right? And spin is expressed by S. So in this case, I am just giving you the short understanding. You will learn it in deeply. From this L, some symbol is coming. There is capital L. Just small s just stands for like SPDF, small orbitals, S orbital, P orbital, D orbital, F orbital. Just like capital S stands for capital S, capital P, capital D, capital F, all capitals. Okay, fine. And from S, we have to calculate one thing that is called spin multiplicity. You know what is the electronic spin? It could be plus half or minus half. Multiplicity. Spin multiplicity is defined as capital S, which is equals to 2 small s into 1 plus 1. Okay, the small s is the spin. It could be plus half, it could be minus half. Fine. So what two parameters I am talking about? One is L. L is nothing but in which orbital it is there. Since this is in the s orbital, so L will be 0. You know, for s orbital L is 0, so its capital symbol will be capital S. Fine. And since there is only one electron, so its S will be capital S. Spin multiplicity will be 2 into. So since one electron is there, only plus half is contributing. If there is another electron, then minus half will be there. Plus half, plus minus half. Okay. So if there is 5 electrons, you have to add for all the spins of the all 5 electrons. Okay. So in this case, since I have only one electron, I am calculating using this one. So 2 to 1, so it is 2. So spin multiplicity is 2. Okay. Now I have to calculate this is the orbital contribution. You know that orbital contribution, but in some cases it is spin contribution. But in some cases it is seen that there is a condition of this spin orbit coupling. We will learn it in details. It is a very interesting topic. We will learn in detail what is spin orbit coupling. Just for this case, you must know there is another quantum number J, which is defined as numbers from L plus S to L minus S. It can have any value, L plus S to L minus S. What is this L? For S orbital, this is 0. For P orbital, this is 1. Just like the azimuthal quantum number, this L. Okay. And what is S? This S is not this S. This is small s. I am writing it small s. If it was capital S, I would write it in the capital. So this S is the spin. Okay. So for this case, 3s case, you have seen what is my S? S is 0. Sorry, L is 0. Because I have S. Okay. Plus S is only one electron, so half. So I have only one J value. This is half. So J equals to half. J equals to half. Fine. So I'm just writing it here. I have a state, then the state is represented by this term symbol. This is the term. The term is what? It is written as your L will be in the middle, like here your L will be S. Also term symbol will be, I am writing here, term symbol will be like equals to your L will be there. So this side will be 2s plus 1, that is the spin multiplicity. Here this capital S will be there, and here this side will be J. Okay, have you got that? The term symbol is just like your L will be there. On the upper side it will be spin multiplicity, what I have talked about, and in the bottom side there will be J. So for 3s you have seen, just writing this way, this writing the term symbol, you can see here that your my 2s plus 1, what is the value? It is 2. So I am writing 2s. What will be a J value? I have calculated it to be half. Okay. Now for 3p case, let's see how much you have understand. What will be the L value for 3p? Anybody? Anybody? Try it. Are you guys there?
Yes, sir.
Yeah. So what will be the L value for 3p? See what I have shown here for S. Okay. Since S means S orbital has azimuthal quantum number L equal to 0. Okay. So that's why since L equal to 0, I have taken this capital L as capital S. Similarly, I have for p orbital, you know what is the value of L for p orbital?
1, sir.
1. So my capital L will be just 1. Okay. So it will signify me capital P or capital P. Just like the capital S, here will be capital P. Okay. Now, okay, so why I am involved, why I am interested with the 3p orbital? Because whenever you are exciting an electron, whenever you are taking sodium chloride to light, you are giving thermal energy. Okay, you are giving energy. So this electron will jump to the upper level. You know, whenever you are giving the energy to an electron, it is going to the upper level. So when if you are giving energy to the S1, so this electron will go to the next level. Which is the next level? Next level is 3p. That's why we are much more interested in 3p. Okay, you have got this answer, that why we are interested in 3p and we are calculating this term symbol for 3p also. Okay, so what will be the S? Capital S? Anybody? Only one electron. This one electron will be there, right? Whenever you are exciting, you have only one electron in the outer shell. If you excite, this electron will go out. So only one electron will go out. So spin will be,
Sir,
yes,
sir, 2.
yes, S will be 2. Just like this S case, this case, because the same electron is involved. One electron, only one electron is involved. Fine. So this is the spin multiplicity, that is 2. So what will be the J value? I have got L value. I have got capital S value. My small s is nothing but half. So what I have said, my J value will be L plus small s. This is small s. Okay. I should have written this in this way, so it will be clear for you. This is small s. Okay. So my values will be from 1 plus 1 by 2 to 1 minus 1 by 2. right? So how many j values I have? 3 by 2 and 2 1 by 2, because there is only one value. 3 by 2, next value is 1 by 2. Okay, do you understand that, everybody?
Yes, sir.
So how many j values I am getting in this case?
2.
2 j values, and which is these two values are coming for 3p level. So whenever there is a coupling between electron orbital and spin angular momentum, or we will discuss it as a spin orbit coupling or RS coupling, you have basically learn, or you will learn this RS coupling, this 3p level into will split into 2 level. So I am writing the symbol. What will be the symbols? One will be 2 capital P. You can see here capital P. Why this is 2 is coming? Due to this spin multiplicity. S is 2. S is 2. This 2 is coming. And what will be my J? For this lower lying state, the J will be higher one. Okay. So, oh sorry, it will be the lower one. Cleared that. Okay. So this will be this one. Another state will be same thing, 3p, and there will be just what will be there? There will be 3 by 2 term, because you have seen here there is 2 j values. Okay, so 2 j values will give me 2 states, right? So, and do you know how much is the difference between these two energy states? This is nearly, very nearly, if I am not wrong, this is nearly 2.1 MeV. Your room temperature is 25 mega electron volt, 25 to 30 mega electron volt, milli electron volt. Okay, 25 to 30 milli electron volt is your room temperature energy. But in the energy difference between these two levels of sodium, it's just 2.1 milli electron volt. That means at room temperature or even below room temperature, these two states can be populated. So whenever you are exciting, you are populating basically these two states. So emission is coming from this one, as well as emission is coming from this one. So that's why you see two lines in emission. So have you got that point?
Yes, sir.
Is it clear why these two lines are coming in sodium?
Yes, sir.
Okay, fine. Okay. So you have got the answer that this yellow color is coming. Why yellow is coming and why it is called D line, I have explained you, and why it is doublet, I have explained you using the term symbol. Now you are clear about that. Okay. So as for today's discussion, all the 10 questions I have covered today, and it will help you to solve your own assignments. So do anybody have any question regarding all these 10 questions?
No, sir. No, sir.
Okay. Okay, fine. So I am stopping the presentation. It was a very good session for the basic day, for the very first day of week 1. So since nobody has any questions, so we can conclude the session here, and we'll meet next Tuesday, the same time, 7 to 9, and we'll solve week 2 assignment, some problems regarding week 2 assignment, and how we can solve this. I will give you ideas, and if you have any queries anytime, you can mail me. Okay, so I will explain that to you. It's fine.
Yes, sir.
Okay, so I am stopping the recording.
Thank you, sir.